Hello, welcome back to our lecture. Today we'll be talking about measurements and things associated with the measurements. We'll start off with talking about the types of measurements you have, talk about the units and the numbers from the measurement. Then we move on to talk about the significant figures and precision associated with a measurement. We'll end up with talking about how you can make your units be magnified or shrunk down using prefixes. So let's start. Measurements are an important part of chemistry and, in fact, in all sciences. Without measurements, we will not have any of the sciences. But of course, measurements is not confined to chemistry. You can see measurements in your everyday life. So let's start this unit talking about some measurements that you are familiar with. For example, this 2-liter bottle of soda is a measurement of volume. The stopwatch is a measurement of time. The scale is a measurement of weight, and this ruler is a measurement of length. In all measurements, there are two important factors. There is the number itself and then unit. So for example, in the mass of the turtle or the weight of the turtle, 320.94 grams. The 320.94 is the number, and we'll talk about that in a minute, and the grams is the unit. In the same case here, this man's height is about, if you were to estimate, 5 feet. The 5 is a number and the feet is the unit. Now if you notice there, I mentioned two units. One is gram and one is feet. It turns out these two units belong to different systems of units. One is the English system and the other one is called the metric system. The metric system is a system of units that is used widely by scientists and health professionals around the world. In fact, only the United States and a couple of other countries still use the English system. Well, in addition to the metric system that is important in chemistry and in the other sciences, the international system is another unit that is important. The international system is abbreviated as SI. The S is system, I is international. Unit is actually derived from the metric units. Now, because we are in the United States, we are very familiar with the English system. So, for example, for length, volume, mass, temperature, and time, these things we can measure. What are the units that you are familiar with? For example, what's a familiar units for length? Like we said, feet and inches. For volume, you can think about gallons and quarts. For mass, you think about maybe pounds. For temperature, we know about the Fahrenheit. And for time, well, time, seconds, hours, right? So let's see how is that different in the metric system and in the SI system. The basic unit for length in the metric system is the meter. If you're not so familiar with the meter, you can think about a meter is about a length of a yardstick. And the abbreviation for a meter is a lowercase m. And it turns out in the SI unit, meter is also the basic unit. Now moving on to volume, the basic unit for volume is liters, with the uppercase L to signify liters. You are probably familiar with liter. For example, your standard bottle of soda is probably 2 liters, right? The SI unit for volume is what we call the cubic meter, m cubed. We probably would not use that unit often. For mass, we have grams, and a gram is actually very small. The units of gram, like for example, a nickel, it weighs about 5 grams. For the SI unit, it goes a little bit bigger, called a kilogram. Now here's a little preview to what we'll talk about later on. That topic is prefixes. Kilo here just means 1,000. So if you put the word kilo in front of something, you multiply that something by 1,000. So kilogram is basically 1,000 gram. So the SI unit for mass is 1,000 times larger. The abbreviation for kilogram is kg, lowercase. Now if you want to go to temperature, in the lab you will usually measure in Celsius, in degrees Celsius. The degree sign is there with the uppercase C. Okay, and we'll talk about temperatures in the next unit. For the SI unit of temperature, it is Kelvin, abbreviated uppercase K. Now sometimes in this class you may do calculations that may use Celsius, that's fine, but in other cases you may have to use Kelvin, and we'll talk about it when we come to that scenario. The metric unit for time is seconds, lowercase s. That's just the basic unit of time, and it turns out SI is also seconds, so nothing new there. Now remember I said that there are two important components in a measurement. First is the unit, and second is the number itself. We just finished talking a little bit about the units. Now let's talk about some aspects about the numbers in your measurement. When you measure something, there are two ways to measure it. One is digital and the second is analog. Well, as you see here from the scale, the weight of that coin is 5.01 grams. That's something that is a digital measurement. Whatever you see displayed is what you record. Now it's a little different when you go to an analog scale. For example, this ruler here. You have to develop a skill to read this measurement correctly. For now, let's just say that it's 4.5 centimeters. Now when you measure volume in the lab, for example, you have to develop another skill. It is also an analog, but you have to develop another skill, is to read it from eye level. The bottom part of the surface of that water has a special name, and we call that the meniscus. So when you read the volume in a graduate cylinder, for example, you have to read at eye level of the meniscus. So in this case, the bottom line there, I would read this at 4.55 milliliters. Now we won't go into detail on how we got that. You may go back to this slide later to confirm that measurement after we talk about how to read analog scales. So let's start. Now whether you make measurements from a digital instrument or an analog instrument, whatever you record is something called a measured numbers. Now measured numbers are those just obtained when a quantity is measured using an instrument. It's pretty straightforward to make measurements from a digital instrument. It's a little bit trickier to take measurements from an analog instrument. So let's spend some time on that. So for example, if I have a ruler here and I want to measure the length of this wooden stick, what would you record the length of this wooden stick? Okay. The first thing I want to say is the markings. The markings is every 1 centimeter, and you see that the length of this stick is between 4 to 5 centimeters. Now would you say that this is 4 centimeters or 5 centimeters? There's no marking in between, so how can we know? Well, we can simply guess that this is 4.5 centimeters, but if you want to be more systematic in your guessing, you want to make these smaller imaginary markings. And it's best to divide things up into 10, right? Because if you have the smallest marking to be 1 centimeter, if you divide it into 10, each of those lines represent 0.1 centimeters. You see how that works? 1 divided by 10 is a tenth, or 0.1. So now if you count the little red marks after the 4, you see 1, 2, 3, 4, 5. 5, it goes to the 5th red mark. So I would estimate this to be 4.5 centimeters. Again, those smaller markings are the imaginary markings. So I will record this measurement as 4.5 centimeters. In any measurement, there's always the unit. Don't ever write a measurement as 4.5. You need that unit. And the second part of that is the number. And here is something I'm going to introduce to you. It turns out that this number has two significant figures. Let's first define what significant figures are. Significant figures are all the digits in a measured number. And we just talked about what measured numbers are, right? So in this case, 4.5, the 4 and the 5 are both significant figures. Now, what's the significance of a significant figures? Well, it tells us how precise the measuring device was. So let's go take a look at an example. Let's take a look at that wooden stick again and measure its length using two types of ruler, ruler A and ruler B. Notice what's the difference between ruler A and ruler B, right? In ruler A, the smallest marking is how much? 1 centimeters. In ruler B, what is the smallest marking? Not 1 centimeters, right? It's, for example, from 4 to 5, that's 1 centimeter, but notice how many markings there are. There are 10 divisions in there. So the smallest marking, meaning the marking from this guy to this guy, from this guy to this guy, those are the smallest markings, right? that's a 0.1 centimeters. Again, how do I know it's 0.1? From here to here is 1 centimeter, and if this 1 is divided by 10 small pieces, each piece represents 0.1 centimeters. So again, the difference in A is that this is 1 centimeter is the smallest marking. In B, it is 0.1 centimeters is the smallest marking. All right, if we go back to our measurements of A, we said that was 4.5 centimeters is the length of the stick. Again, the smallest marking was 1 centimeter. In B, though, we can say the measurement was 4.55 centimeters. Why? Because the smallest marking is 0.1. So you can say this is 4, this is 4.5, this is 4.6. So we know the stick's length is between 4.5 and 4.6, right? So we are sure to the 10th position. So then we just make an extra guess. Let's say it's between 4.5 and 4.6. What's between 4.5 and 4.6? Well, 4.55, right? So we are sure to the 10th position, so we make an extra guess to the 100th position. Same thing here. We were sure to the 1's position, right? Because the smallest marking was 1 centimeter. So we make an extra guess to the 10th position. Again, the smallest marking here was 0.1, which is to the 10th position. So we make an extra guess to the 100th position. You see, the more significant figures you have, the more decimal places you have, the more precise the ruler you are using. So it's very important to know how many significant figures to record in your measurement. Another thing I want to point out to you is why I didn't make those imaginary markings in ruler B. Remember in ruler A, there was a lot of space between 4 and 5 centimeters, so I can make 10 divisions. While in ruler B, the smallest marking was between 4.5 and 4.6, and I can't really make 10 divisions in there. So instead I make 2 divisions. So if you make 2 divisions, you just divide it in half, right? So because each of these smallest marking is 0.1 centimeters, if I divide it in half, each one would be 0.05 centimeters. So that is why I would say that this is 4.50, this is 4.55, this is 4.60. Let's try C. What would you record the length of the stick in C was? I'll give you some time. Did you say 3 centimeters? That was the tricky one. If you did, it is not correct, right? Again, what was the smallest marking you should ask yourself? So the smallest marking was 1 centimeter, which is in the 1's place. So you must make your recording to be in the 10th position. So the actual measurement turns out to be 3.0 centimeters. Is there a difference between 3 and 3.0? No, right? But there is a difference in terms of significant figures and in terms of precision of the instrument you are using. So we need to make sure that we are recording properly so that someone who's reading what we record understands what kind of instrument we were using. So that when someone sees this measurement, they will say, this has 2 significant figures and it's recorded to the 10th position. So that means the ruler must have been marked to the 1's only. Okay? Now here's a challenge question for you. For those of you who already thought about it, good for you. So the challenge question is, let's say someone recorded properly and they did record the length of a stick to be 3 centimeters. So then what must the ruler markings look like if that student was correct? I'll give you some time to think about that, and we'll talk about that in class. Okay, so in our last example, we found that 0 was significant, and it turns out not all zeros are created equal. Some zeros are significant, and some zeros are not. They're just placeholders. So let's take a look at 2 examples to flesh out the differences between zeros that are significant and zeros that are not. In our example, we are going to measure 2 sticks of different length using 2 rulers. In the first one, you can see that the ruler being used has the smallest marking of 100 centimeters, right? For every 300 to 400, that's 100, 400 to 500, that's 100 centimeters. So again, if we were to make imaginary divisions, we can imagine that each small division here will represent 10 centimeters, okay? Giving us an estimation value of 450 centimeter as the measurement. In our second example here, the ruler that is being used has the smallest marking of 1 centimeters. From 103 to 104 is 1 centimeters. 104 to 105 is 1 centimeter. Right? So our imaginary markings, if we make 10 of them again, would now represent only 0.1 centimeters. Again, this falls into the fifth imaginary marking, so we can make the measurement of this being 104.5 centimeters. Again, the way we write and record measurements tell you the precision of the instrument. In the second case, the numbers is significant to the tenths value. Whereas in the case of the first ruler, the precision is only to the tens value. Whatever number that follows that isn't significant anymore. So it turns out that 0 is not significant. It's merely a placeholder, because without it, it'll be 45, and we don't want to say this is 45 centimeters. We want to say this is 450 centimeters. In the second case, this 0, because the number is significant all the way to the tenths value, anything beyond that, anything greater than that is significant, right? So this 0 is significant. So there are rules to counting significant figures, so let's go over them systematically. Let's go over this one by one. A number is a significant figure if it is a not a 0, right? So when any time you write something down that it's not a 0, that number is considered significant. So our example here is 4.5 grams. That 4 is significant, that 5 is significant. So there's two significant figures there. Okay. So any number that is non-zero is considered significant. So the rest we have to worry about are the zeros, right? So when is a 0 significant? In case B, we see that a 0 is significant if it is between non-zero digits, right? So in the measured number of 205 meters here, these are non-zeros. There's a 0 between two non-zeros, so this 0 is significant. So to count significant figures in this number, we would say 1, 2, 3. There are 3 significant figures. What are other cases where zeros are significant? In case C, a 0 is significant if it is at the end of a decimal number. So anytime you have a decimal number, this is considered a decimal number, right? 50 point. Whenever you see that point, that makes it a decimal number. Any zeros that are at the end, we call them trailing zeros. They are significant. So in 50 point, 5 is significant and 0 is significant. Now that whether that 0 is before or after decimal, it doesn't matter. If it is at the end, it is trailing, it is significant. So in 25 degrees Celsius, 25.0, that 0 is significant. Once again, this has 2 sig figs. This has 3 sig figs. In the last case, this is a catch-all kind of case. Any number that is written in scientific notation, whether 0 or non-zero, is significant. So in this case, 4.8 times 10 to the 5th, 4.8, both of those, they're non-zero, so automatically make them significant. But 5.70 times 10 to the negative 3 grams, their second example here, that 5 and 7, again, non-zeros are significant. That 0 is going to be significant. Okay, anytime you write 0 in a scientific notation, it's going to be significant. Now, the opposite rule is a rule when a 0 is not significant. These two rules are opposite of each other. So if you remember one set, you then automatically remember the other set. Okay, so a 0 is not significant if it is A, at the beginning of a decimal number. Remember we talked about decimal numbers before, and if they're at the zeros at the end, they are significant. Well, in this case, this is the opposite. If a 0 is in the beginning of a decimal number, we call them leading zeros. These zeros are insignificant, right? So for example, in the number 0.0004 seconds, the only number that is significant is that 4. All these zeros are just placeholder. They are not significant. Okay. In the second case, 0 is not significant if it is used as a placeholder in a large number without a decimal point. So again, if you have a number that is not a decimal, so it's a large number, the zeros in this case that are at the end to call the trailing zeros, these zeros are insignificant. So in 850,000, only the 8 and the 5 are significant. All the zeros are insignificant. So these rules are kind of opposite of each other, right? Again, let me rephrase. If you have a decimal, leading zeros are insignificant. If you have a large number without a decimal, trailing zeros are insignificant. They are opposite of each other. If you remember those two rules, you will be set to go. All right, so let's take a look at some examples of how to determine how many significant figures there are in a measurement. Number 1, 122.35 meters. All of those are non-zeros, right? So they are all significant. You have 5 significant figures there. Number 2, 5.008 kilograms. All right, you got a 5 and 8. Those are definitely significant. What about those zeros? Again, those zeros are in between significant figures, so they are significant, right? So that's 4 significant figures. Number 3, 0.075 centimeters. What kind of number, you ask yourself? This is a decimal number. In a decimal number, if you have leading zeros, they are insignificant. Very good. So only the 7 and the 5 are significant. So you have 2 SFs there. Number 4, 16.00 gram. Again, you ask yourself what kind of number. This is a decimal number. And zeros that are trailing in a decimal number, trailing at the end, they are significant. So all of those numbers are significant. So you have 4 sig figs there. And last example here, you have 86,400 seconds. Okay, ask yourself, is that a decimal? Nope, that's not a decimal number. That's a whole number that's large. In a large number, trailing zeros are insignificant. That's correct. So you have only 8, 6, and 4 as significant figures. So you have 3 sig figs. So 0 are not significant figures. Go ahead and just practice with this. Once you get this, this becomes very easy and will be very useful for you as you record your answers throughout the semester. Okay, now here's a trickier case of taking measurements. How would you measure this? Okay, let's go back to our analysis again. The smallest marking here is 100 centimeters. Because it is 100 centimeter, the smallest marking is in the 100s, so we can make an extra guess to the tens, right? So we should record this to the tens value. But the recording is 300. If I just write 300, then these 2 zeros are both trailing zeros. So it turns out only one number is significant. But I just want to make my recording to signify that it is only significant to the tens. So only that first zero is significant. So what do we do? It turns out there's another way of recording this measurement. You can also say it is 3.0 times 10 to the 2. What is 3.0 times 10 to the 2? That's basically 300 in value, right? But in this way of writing it, you can write this 0 and leave this 0 out, giving you 2 sig figs. In this way of writing the number, we are true to the value of 300, but we're also true to being 2 sig figs in measurement. Okay? So in tricky cases like this one, you want to use scientific notation. You don't see it often, but when you do, it is made most clear if you write it in scientific notation. Okay, here's a checkpoint for you. So I will frequently have these questions to have you gauge your understanding of what we just discussed so far. And these kind of questions are very similar to the questions you will see on the test. So it's good to do these checkpoint questions. So in this question, I asked you, which is the correct way to record the following measurement to 2 significant figures? So if I give you this number, 0.00400 centimeters, how can you record this to 2 significant figures? We can write 0.00, all of those zeros are insignificant. That 4 is 1 significant, so we can include one more figure to be significant. That is the 0 here. So 0.0040 is our answer right here. That's the only option that has the good answer. But as any good test taker, you always want to consider the whole answer. What is 4.0 times 10 to the negative 3 here all about? Well, that's just writing this number in scientific notation, right? If you were to move this 1, 2, 3 over to the right, you would get 4.0 times 10 to the negative 3. So these are representations of the same number. And this also gives you 2 sig figs. So yes, the answer is B. So good job if you got that. If not, review and practice some more. All right, so we're moving on now to do some math with our sig figs. In this class, we will do a lot of math calculations, and the sig figs don't just disappear when you do calculations, they carry on. So they carry on in two fashions. When you multiply and divide, you follow one set of rules, and when you add and subtract, you follow another set of rules. So let's talk about what happens when you multiply and divide. So let's read this. In a multiplication or division of measurements, the final answer is written so that it has the same number of sig figs as the measurement with the fewest significant figures. Okay, let's break that down. You have two numbers you want to multiply to each other, and you get a number out. And that number you have to write with a certain number of sig figs. So the rule is choose the one with fewer significant figures. So in this case, you have 1, 2, 3, 4 versus 1, 2, 1, 2. So you have 4 versus 2, so your answer must have only 2 sig figs. So when you punch this into your calculator, you will get a number that looks like this, 8.631. But if you write this on the test, you will get some points taken off because you have not considered significant figures. Again, we can only have 2 sig figs in our answer because there are only 2 sig figs in this measured number in our calculation. Okay, so this rounds down to 8.6, dropping the hundreds and the thousands place. If you need a reminder on how to do this rounding, go back to our first lecture and take a look at math review there. Okay, let's continue here. In our second example here, when you do this multiplication of 24.66 times 0.36, you get this number. Okay, again, how many sig figs should we have in our final answer? 2, right? Again, because this is only 2 sig figs. So we can only go from 1, you count 1, 2. That's 2 sig figs. But do you write 8.8? No, right? It's 8.9 because when you round, you look at 7 and you round it up, bump this up by 1, dropping the rest. So that becomes 8.9 meters squared. Notice that units are always important. That's why I include there. When you do math with units, the units also multiply each other. So meters times meter is meters squared. Okay, let's take a look at the third example here. 5.0 grams divided by 3.00 ml. On your calculator, you get a number that's 1.666666. Now this is where this rule is very useful because sometimes you have an answer that is very, very long, and different people will cut off a different place. Some people write 1.66, some people write 1.666666, and so on and so forth. So having this rule is very good because it limits us, and everyone will have the same right answer. Okay, again, so following this rule, this has 2 sig figs, 1, 2. This has 3 sig figs, 1, 2, 3. So our answer should have only 2 sig figs. Right? So our answer should be 1.7 grams per mil. Right? Awesome. All right, last example here. 6.0 grams divided by 2.00 ml. And your calculator should say 3, and you record 3 grams per mil. Is that correct though? Nope. All right, because again, our lowest sig fig is 2 versus 3, so 2 is the number you should have in your final answer. So how do you make 3 to become 2 sig figs? 3.0, right? Remember, 3 and 3.0 are not different in value, but they are different in the number of significant figures. Cool? All right. Hopefully you get more practice with that from your textbook or from your homework. That's going to really help you get all the points you can on the test, because when you write your final answer on the test and it doesn't have the correct number of significant figures, you will have points deducted. Now let's move on to the second set of rules governing sig figs and calculations. When you add and subtract, the rule is that the final answer that is written must have the same number of decimal places as the measurement with the fewest decimal places. Now the key difference here is fewest decimal places, not fewest significant figures. Okay, so fewest decimal places. So let's take a look as an example. Let's say you measure the length of 2 sticks and you use 2 different rulers. I don't know why you would, but you did. And so one is more precise. One is precise to the hundreds and one is precise to the tens only. When you add these two numbers together, you get a display in your calculator as 7.54. But this doesn't follow the rules for sig figs. So according to this rule, the fewest decimal place you have to look at this is the hundredths place and this is the tenths place, so your answer must be in the tenths place because that's fewer by 1 decimal place. So you drop this 4 and your answer is 7.5. Okay, so what about this case? And so how would sig figs rules apply? At first glance, you might think to yourself, oh, okay, it's mostly a division problem, so I'm going to use the division multiplication rules for applying sig figs. So I say to myself, this has 4 sig figs, this has 3 sig figs, this has 3 sig figs, so therefore my final answer should have 3 sig figs. And in fact, that would be the wrong conclusion. Right? So to solve a problem like this, you just simply follow the order of operations, applying sig figs at every step that you go. Okay, so let's start. Orders operation says you first solve what is in the parentheses first. So 22.1 minus 19.5 turns out to be 2.6. Okay, so in this case, the significant rules tells us that this is a subtraction problem, so you keep the place value that is the fewest. In this case, this is the tenths and this is the tenths, so your answer, they're both equal, so that your answer should be in the tenths value. From this, you get a new number that has its own significant figures. This has 1, 2 significant figures. Okay, so now you're dealing with basically a division problem between 2 numbers, each with their own significant numbers. Right? So that rule says the answer has to be the same number of significant figures as the value with the least amount of sig figs. In this case, 4 versus 2. So 2 wins, so your answer should have 2 sig figs. Okay, so do this in your calculator. You should get 0.92346 and so on. It's a longer answer. But we know, but we don't care since we know that we only need 2 sig figs to come out of this. So to write our final answer again, we write 0.92 only, because that's our first and our second sig fig. The 3 just drops out because of rounding rules. We box it to make it an official answer. Okay, and I want to remind you to round only at the end of the final mathematical calculation, but to keep track of sig figs for intermediate calculations. And throughout the semester, we'll do a lot of examples so you see where this is in use. Okay, so we talked a lot about sig figs, but not all numbers have significant figures. Okay, so it turns out sig figs only apply to numbers that are from measured number. The other types of number are called exact numbers, and they do not have sig figs. Okay, exact numbers, what are they? Exact numbers are obtained by counting items or using a definition. So when you count something, you're not using any instrument to measure it, or when you're using a definition, again, you're not using an instrument to measure it. So let's talk about some examples where exact numbers can come from. Exact numbers can come from counting individual objects, as we said before. So an example here is when you count 24 students in a classroom, that 2 and that 4, you don't say there's 2 sig figs in there. You just say that is an exact number. So no sig figs or infinite amount of sig figs. They basically it doesn't apply. Okay. A second place you can find exact numbers is from a definition that compares two units in the same measuring system. For example, 60 minutes in 1 hour. There's no sig figs applied there because that's a definition. Sometimes exact numbers can also come from comparing two units in different measuring systems, and those times are rare, and then you would see an annotation that it is an exact number. If it doesn't say it's an exact number, assume that it is not an exact number and it's a measured number. And the third case where you can see exact numbers is when you see a number, an integer, that part of equation. So for example, area is equal to pi r squared. That pi is 3.14159 blah blah blah. That has no significant figures there. So you may ask yourself, what's the point in knowing something is an exact number versus a measured number? It's because you need to consider it when you do calculations. Remember, sig figs, when you do calculations, the multiplication or division, subtraction, division, you have to think about sig figs. So if you do a calculation with exact numbers, you have to recognize that and say to yourself that sig figs do not apply to it. So for example here, when you want to convert grams into kilograms, so I'm just going to ignore how to set this up as a conversion factor problem because we'll cover that later on. And we'll just jump to the point where we have set up a math problem. Basically, look at this as a math problem. It's a multiplication problem where you have this number multiplied by this number divided by this number. Okay, so these are all numbers being multiplied and divided, and you think back to your rules of multiplication and division for sig figs. You think to yourself, okay, the final answer must have the number of sig figs of the fewest sig figs of the measured number. And so you have to keep that in mind, okay? The numbers turns out to be 0.32094, and you might be tempted to say, oh, okay, a sig fig tool tells me that I have to have only one sig fig because this is one sig fig, this is one sig fig, this is 1, 2, 3, 4, 5 sig figs, so my answer should be 0.3 kilogram. No, right? Because you should recognize that this 1 and this 1,000, these are definitions of each other. Because they are a definition of each other, they are exact numbers. So there's only one measured number in this, and this measured number has 5 significant figures, so your answer has 5 significant figures. 1, 2, 3, 4, 5. Yeah? Okay, so that's why they're important. 5 sig figs. Again, not 0.3 kilogram. Not 1 sig fig. This brings us to our third and last part of our lecture today, is talking about prefixes and equalities. We had a glimpse of a prefix, what prefixes are already when we talked about units of mass in the SI system was kilogram, right? That kilo is a prefix. So a prefix, like in your grammar class, is a root word that goes in front of a word, right? So in chemistry, a prefix is something that is placed in front of any metric unit to increase it or decrease it by a factor of 10, which makes it very convenient. So we don't have to write so many numbers. So for example, the width of a hair on a person can be measured, and it turns out that it is 0.00008 meters. Now you see how cumbersome it is to say 0.000008 meters. So instead, sometimes we write in scientific notation. We write as 8 times 10 to negative 6 meters. Remember scientific notation, going to the right, 1, 2, 3, 4, 5, 6 times makes it 10 to negative 6. 10 to negative something, again, makes it very small. Okay, so that makes it easier to write, but still, 8 times 10 to negative 6 meter is still not efficient of a way of speaking. So we come up with the prefix micro, and that micro basically replaces 10 to negative 6. So we say this is 8 micrometer. See how that prefix changes, is put in front of meter to make the unit now micrometer, which is a very small unit because it's 10 to the negative 6, so that's 8 micrometer. There are some prefixes that makes things that magnify things, and there are some prefixes that shrink things. So talk about things that make them big. Okay, the first one we saw already is kilo. When you want to make 1,000-fold of something, you put the symbol K in front of it and make it kilo. To make it kilo, to make it times by 1,000. So the scientific notation there is 10 to the third. Now in chemistry, we hardly go to mega and giga, but it's good to know. One place where you may have heard of it is in your computer. All right, you have a byte. You may not know of a kilobyte because things nowadays are so big that you don't see it in kilobytes, but you are familiar with what? Megabyte, right? And gigabyte. So megabyte basically is 1,000,000 bytes, right? So that's 1,000,000. If you write capital M in front of something, that makes it 1,000,000 times 10 to the 6th power. And giga is a billion. If you have a gigabyte of something, you have 1,000,000,000 bytes of it. The scientific notation there is 10 times to the 9th. Okay, now let's talk about the other set of prefixes. These prefixes make things come smaller. The first one is deci. Think about the root word deca, decade, 10, right? 10. So deci here with the symbol D makes it smaller by 10-fold to become a tenth of something. So the numerical value you multiply it would be 0.1. Scientific notation is 10 to the negative 1. Centi, where have you heard century? Century is 100 years, right? So centi with the symbol lowercase c would be 100th of something. So multiply by 0.01, 100ths of something. 100ths of something, so that's 1, 2 decimal places over. And we say that's 10 to the negative 2. Milli, abbreviated, symbolized with m, lowercase, would be 1,000th, right? 1 in 1,000 is 0.001, which is 10 to the negative 3. Micro, right? Something very small is micro. Like a microscope is to look at something very small. When you take your biology class on small organisms like bacteria, it might be called microbiology, right? So on the scale, we use a symbol, the Greek letter mu, to represent micro, and it is actually 1 in 1,000,000. Okay, so that's 0.000001 or 10 to the negative 6. Now it goes even smaller, right? You can go to 10 to the negative 9 for nano and 10 to the negative 12 for pico. Okay, that's very, very small. On the size of atoms now, not even microorganism, we're talking about atoms. All right. Now, with this long list, I don't want you to be too overwhelmed, so I'm highlighting only the prefixes that are very common in this class, and you are held responsible for knowing it. You should know its name, you should know its symbol, you should know its numerical value, and its scientific notation. Okay, again, so you're responsible for kilo, deci, centi, milli, and micro. Again, as a summary, these prefixes on the top here is to increase the size of the unit, and the prefixes on the bottom table is to decrease the size of the unit. Alright, let's take a look at how to use these prefixes, and we'll take a baby step and just figure out how to use the prefixes to write equalities. Right? So, for example, if I wanted to write the equality between a kilogram and a gram, right? Remember what an equality is, and we'll learn this later on some more too. An equality, it means whatever's on the left-hand side is equal to whatever's on the right-hand side. Okay? So to write equalities from prefixes, all you have to do is replace that prefix with what that prefix means or what it stands for. For example, K, kilo. What does kilo stands for? If you recall back, kilo means it's 10 to the third or 1,000, right? So the equality of that would look like this. 1 kilogram is equal to 10 to the third gram, or you like to write it like this, it's 1 kilogram equals to 1,000 gram. Again, this is an equality because whatever's on the left-hand side is equal to on the right-hand side. The left-hand side is kilo, which means 1,000, so 1,000 gram. Replace that K with the word 1,000. Is equal to 1,000 gram. All right, let's try another one. What is the equality you can write from centimeters in meter? You ask yourself, 1 centimeters is equal to what meter? Again, just simply replace the prefix centi, but still retain the base unit of meters. Remember, centi is 1 out of 100, right? 100th. So 1 centimeter is 1/100th of a meter, and remember that 100th is 10 to the negative 2. So you could write this equality, and another form is this: 1 centimeters is equal to 0.01 meters. Lastly, let's try one more time. 1 microliter is equal to what liters? Again, if I ask you to write the equalities between microliter and liter, this is what you should be thinking about. You would ask yourself, okay, micro means 10 to the negative 6. So 1 microliter is equal to 1 times 10 to the negative 6 liters. You see how I did that? Simple as that. Just use that every single time, and you always will write proper equality from prefixes. And that's an important skill later on when you have to write conversion factors from this equality, as we'll learn in the next part. Okay, and lastly, just want to round it out on giving you a view of how that looks like if you write out the number instead of the exponent. Okay? So as alluded to before, prefixes are useful because depending on the scale that you are working on, some prefix might be more useful to you. And so in this slide, I will show you some common units of length and masses and volumes that you will see in chemistry and in this course. We start with the basic length, which is meter. Now, meter is a good unit to use if you were measuring, let's say, the height of somebody, but you wouldn't use a meter stick to, say, measure the width of someone's iris, right? You would use a different. So, for example, the width of someone's eye, you might want to use a centimeter scale or millimeter scale instead. We just talked about writing equalities from prefixes. So we said that 1 centimeter, replacing the centi with 0.01 is equal to 0.01 meter, right? 1 centimeter is 0.01 meter. What if I asked you the opposite? 1 meter is equal to how many centimeter? You can simply say it's 100 centimeter. How do you come about this? 100 of something that is only 1/100th of a meter is equal to the whole thing. That's like almost saying how many halves does it take to make up a whole, right? You will need 2 halves. Or another example that relates to the root center here is pennies. A penny is basically 1/100th of a dollar. So how many pennies do you need to make $1? You need 100 penny, 100 of 100th to make up $1, right? Okay, so both of these are equalities you can use. This one I like to use a lot because you just simply think centi, replace it with this, whereas this kind of equality you kind of have to think in a different way. So I know some of you have been taught to think this way, so it's fine if you like it, but if you don't, you can start thinking about it, writing equalities this way. Okay. Now let's talk about some common units found in volumes and masses. In the health field, you might see this unit for volume, deciliter, and the equality there is 1 deciliter is equal to 0.1 liters, or in other terms, 10 deciliters is equal to 1 liter. Remember, deci means it's a smaller unit than the liter itself. So you need a lot, 10 of it, to equal 1 of that. That's how I always think about it. A lot of the smaller unit to equal 1 of the bigger unit. Because some students might be mistaken and write that 1 deciliter is equal to 10 liters. That's a common mistake. I just want you to avoid doing that. Another common unit for volume is centimeters cube. You might also see this as 1 cc for cubic centimeter. You will see that in health fields a lot. And that turns out to be equal to 1 milliliter. That's one equality that's useful to know. In terms of masses, we will see masses in very different scales. You can see in grams, kilograms, milligrams, and even if you go down smaller, you will see in micrograms. And sometimes I just want to point out that it is written as mcg, because sometimes the Greek letter mu for micro is hard to understand or easily mistaken with m, which means milli, and you do not want to confuse micro with milli, right? That's a dosage difference of 1,000, let's say, that could be potentially hazardous if you were to make that mistake. So sometimes people just write mcg, or they just write it out micrograms. All right, so here's again looking at when you want to use these prefixes, depending on the scale that you have. For example, this table of daily values for selected nutrients lists great examples here. You need a lot of protein, so you want to put that in a scale of grams, so 44 grams. Vitamin C, you need less of than protein, so it's in the scale of milligram, so 1,000-fold less. And in vitamin B12, you even need less of that, so you need it in microgram scale, so that's 6 microgram. Okay, so our last checkmark for today. Question is, which prefix is the most appropriate to write 0.000004 meters, right? So if you were to write this, which of the prefixes would be a good scale to cite this number? Well, you notice that this is a smaller scale, so you want to use a prefix that is gonna shrink your number, right? So not mega, because that makes it bigger. So maybe it's milli or it's micro, or it could be none of the above. We'll see. So let's see. How do I make this to be a scale where 4 is just a number? I push the decimals over 1, 2, 3, 4, 5, 6. Ooh, if I push it over 6 times, that's in the range of micro, right? So it turns out that the answer would be C, and you will write this as 4 micrometer. All right, so let's end this with a learning goal recap. So as you read this list, you should also be thinking to yourself, by the end of this lecture, I can do the following. 1, write the names and abbreviations for the metric or SI units used in the measurements of length, volume, mass, temperature, and time. I can take measurements with the correct precision, thinking about smallest markings, thinking about 1 extra digit after the smallest markings made by imaginary markings. I can adjust calculated answers to give the correct number of significant figures, right? Thinking about significant figures with calculation, rounding, and the sorts. And finally, I can use the numerical values of prefixes to write a metric equality. Right, we just did that. All right, so we'll see you in the next lecture.